Hello everyone, and welcome to MillimeterWave. Today we're going to discuss one of the most important components used in microwave and millimeter wave measurement systems, Amplitude Detector. Amplitude detectors are commonly used in radar systems, communication links, electronic warfare equipment, and RF test environments. To properly use a detector, it's important to understand how it responds to RF power, how sensitivity is measured, where compression occurs, and how factors like load impedance and bandwidth affect the performance. Let's start with basics. What is an amplitude detector? An amplitude detector converts RF power into DC voltage. Instead of measuring a high-frequency RF signal directly, the detector produces a low-frequency voltage that can be easily measured using standard instruments. This makes RF power measurement much simpler and more practical. So why do we use a detector? RF signals operate at extremely high frequencies. In most applications, we are not interested in viewing the RF waveform itself. What we usually want to know is the signal's power level or signal strength. An amplitude detector converts RF power into a DC output voltage that is proportional to the input signal, allowing us to measure power quickly and accurately. So how detectors are evaluated? Amplitude detectors are typically characterized using standard RF laboratory equipment. This often includes an RF signal generator, precision attenuators, a calibrated reference measurement chain, and a DC voltmeter and data acquisition system. The process is straightforward. A known RF power is applied to the detector at the waveguide port, and the resulting DC output voltage is measured at the coaxial port. One of the most common detector measurements is sensitivity. A known RF input level is applied, often around -20 dBm. The resulting DC output voltage is then measured. From this data, detector responsivity can be calculated in millivolts per milliwatt. This value indicates how efficiently RF power is converted into DC voltage. As power increases, the detector enters the linear region. In this region, the detector provides a wider operating range, although measurement precision begins to decrease. At even higher power levels, the detector transitions into the logarithmic region. This region provides the greatest dynamic range, but lower sensitivity. Understanding which region the detector is operating in is critical for accurate measurements. As input power continues to increase, the detector begins to compress. For this device, compression typically begins around -15 dBm. Beyond this point, the detector output no longer follows the ideal response curve. Measurement accuracy begins to decrease and output voltage becomes increasingly non-linear. Every detector has a maximum safe input power level. For this detector, the maximum RF input power is 17 dBm. Operating above this level may cause saturation, significant non-linearity, or long-term performance degradation. To maintain measurement accuracy and protect the detector, input power should remain within the specified operating range. At very low signal levels, detector performance is often described by tangential sensitivity. Tangential sensitivity represents the point where a signal can be distinguished above the noise floor. This typically occurs when the signal is approximately 8 decibels above the noise level. This specification helps define the detector's minimum usable signal level. In practical testing, sensitivity is measured by applying a known low-level RF signal, often -20 dBm. The resulting DC voltage is measured and converted into responsivity, expressed in millivolt per milliwatt. These measurements are performed in the small signal region before compression begins to ensure accurate characterization. Another important factor is load impedance. The load connected to the detector output directly affects the detector performance. With a 1 megaohm load, the detector produces a higher output voltage and maximum sensitivity. However, response speed is slower. When using a 50 ohm load, output voltage decreases, but response speed increases significantly. This configuration is often preferred for high-speed measurements. With a 50 ohm load, detector response time can be approximately 1 nanosecond. This fast response makes the detector well suited for pulsed RF signals and time domain measurements. The choice between sensitivity and speed depends on the specific application. Video bandwidth, often referred to as VBW, affects how quickly the detector output responds to signal changes. A wide video bandwidth provides faster response but allows more noise to pass through. A narrow video bandwidth reduces noise and creates a smoother output signal, but response time becomes slower. As with many RF measurements, this is a trade-off between speed and noise performance. Let us review the key points. An amplitude detector converts RF power into a DC voltage that is easy to measure. Because RF signals operate at extremely high frequencies, detectors provide a practical way to measure signal strength and power. At low power levels, the detector operates in the square law region, where sensitivity and accuracy are highest. As power increases, it enters the linear region, providing greater dynamic range. At higher levels, the detector operates in logarithmic region, offering the widest measurement range but reduced sensitivity. Compression begins around -15 dBm and maximum safe input power is 17 dBm. Sensitivity is typically measured at low power levels such as -20 dBm and expressed as responsivity in millivolt per milliwatt. Load impedance and video bandwidth also influence the detector performance. 1 megaohm load provides higher sensitivity, while a 50 ohm load provides faster response, approaching 1 nanosecond. Video bandwidth allows the user to balance measurement speed against noise reduction. MillimeterWave amplitude detectors are designed to provide accurate and reliable RF power measurements across microwave and millimeter wave frequency ranges. Understanding detector operation, sensitivity, compression behavior, and measurement techniques helps ensure accurate and repeatable results. Thank you for watching. For more information about MillimeterWave products and measurement solutions, please visit miwv.com. We will see you in the next video.